It is time for part 2 of chapter 9 here. Post spring break 2021 is when this video is being recorded for lots of excitement of vectors. All right, so let's talk vectors. We're changing gears here. So a lot of concepts in, say, like science and application, they measure certain quantities by their magnitude. So like length is just one number, right? Mass, area, temperature, energy, all those are just a single number. And only one number is really needed. If I'm going to say a length of 7 inches or a length of 5 feet, I just have that one number. Or 5 degrees here, Celsius, right? Celsius. That's what a lot of people use. And that's called a scalar. That single quantity is called a scalar. However, there's also applications like, what if I were to say, oh yeah, you traveled 20 feet. In what direction, right? I want to know what direction, only one direction that you went in. Yeah, I planned that. So a vector is going to give that to us. It's going to give us both direction and that magnitude, that length that we're maybe traveling or something like that, okay? So direction and magnitude. All right. So here we got an example down here. So we have vector PQ, right? And the order matters. Think back to geometry when we had like array, right? Array with that line with the one arrow on it. The order mattered in which you put it. PQ and QP are two different vectors, okay? Now, let's take a look down below here. Actually, backtrack. We got our initial point. We have our terminal point. So there's going to be some new vocab that we're going to be dealing with there. Didn't mean to skip over that. All right, so the vectors PQ, RS, and TU in that graph below, they are all equal because they have the same direction. They're all going in that one direction, right? Okay. And they have the same magnitude. Okay, lovely. So we can see here, these are all going, if you were to go in the X direction, we'd go 1, 2, 3, 4, and then up 1, 2, 3. And all of them are going over 4, up 3, over 4, up 3. So the same magnitude, same direction that they're going. All right, so vectors, they're either denoted with a bold character, see how that V down here is bold, or written with an arrow over the top of the letter. So we have V as a bold letter, or V and then an arrow over the top. A lot of times just like a single little arrow. All right. So we can calculate the direction and the magnitude using math that we already know. All right, we're bringing back some geometry with this one. So the double absolute value bars, sometimes it's single absolute value bars, sometimes it's double. Different books use different notations, so be used to seeing either one. That represents our magnitude, okay? So if I want to find my magnitude here, we're really thinking about it as like you're almost getting the length of this right here. Well, how can we do that? So what if I were to create essentially a right triangle here? Boom. I went over 3 and I went up 2. This looks like our old friend, the Pythagorean theorem. So we would do 3 squared plus 2 squared in the square root. That would give me my magnitude of V. So that'd be 9 plus 4 is 13. So square root of 13 would be my magnitude here. Now, how about our direction? What direction are we going in? One direction. And I do know that it's not just Harry Styles for one direction, okay? Just, come on, if we're going to pick one picture, it's going to be Harry, you know? All right. So for my direction here, I am talking about this angle here that it would make with the positive x-axis. You can reposition a vector to the origin and then have it just go in that direction there and calculate it kind of like we'd calculate with any other kind of trig. Or you can think of it with the right triangle there. I'm looking at that angle there. Well, I've got my opposite and my adjacent sides here. So I'm going to do tangent inverse of 2 over 3. And that's going to equal approximately, I got it written down. Make sure your calculator is in degree mode if it's asking for degrees. If it's asking for radians, use radian mode. We'll use degrees. We have 33.69 degrees for my direction. All right. So we got our magnitude of root 13. We have our direction of 33.69 degrees. Lovely. So Pythagorean theorem, inverse, tangent, those are your two friends for direction and magnitude. Let's keep going. All right, here are some graphical geometric representations of vectors. So we're talking about vector addition here. Okay, so we can add vectors. We do all sorts of, you can add, subtract, multiply, all that good stuff with vectors here. So we're gonna look at addition, and we got a couple different methods here. All right. So the first one, we got our triangle method, or some might call it either head to tail or tip to tail. So we've got the tail here, and then we've got the head, or some will call it the tip, and then we go tail again, it's head. So we just line them up, and I think the description here is very, very nice. So I pause the video, I jot these guys down, and then the result vector would be this green one here of u plus v. So we connect the tail of the first to the head or the tip of the second, okay? And those steps right down there are beautiful. And then we have our parallelogram method. Okay, so we're going to place both vectors at that initial point, the same one there, and we're going to create a parallelogram. And then that parallelogram, I said that weird the first time, the diagonal of it, that would be my resultant vector, u plus v in this case. Lovely. So pause that, jot those down, take a screenshot, whatever you got to do, whatever's best for you in your notes. But I think these are nice representations here. So here's another graph here. We got v plus w. So v is this one right here. And then w, do orange, right there. The initial point of v, which is this, connecting to that terminal point of w. That gives me v plus w. Lovely. All right, so we've got three different vectors here. We have v is this one here. We got w and u. It's a little, but a little blurry, but that's okay. So what we're going to do is, so we have 2w. We'll start with that first example. So you've got three different examples here on the graphs. You notice there's no like x and y axis here. It's just kind of a blank canvas, if you will. So just make sure that when we position these that we have enough room to multiply or add or anything like that. And you'll kind of see, I'll help you through it. Obviously, because I'm making the video. All right, so we want to do 2w. So if I have w, I'll copy that down. Say, here we go, boom, and that goes down 2 and over 2, right? So I go down 2 and over 2, and I end up here. Boom. Now, if I want to do 2w, I'm just going to repeat that again. Is that a voice crack? I don't know. But there is 2w, okay? We're going down 4 and over 4. So that'd be 2w. Lovely. Fantastic. Wonderful. So we just graphed that. Now we can also graph 2v plus 3w. So v goes over 3 and up 2. So I'm going to start that, how about like right here. So I'm going to go over 3 and then up 2, or I could even, and then I'll do it again, over 3 and then up 2. Or, what I was about to say there, I could go over 6, up 4, you know? So, boom, there is 2v, right? So I got v here and I got v here. Then 3w. I'll change colors for that one. So 3w, I'm going to go here, again, and a third time, woo, going down 2 and over 2 each time, right? That one's a little easier to see because it's the same, down and over. And that would be, this is w, 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 and now my resultant vector, the initial point of the first one, the ending point of the second one there, the terminal one there, and boom, we have 2v plus 3w. We are cruising through vectors. We are cruising. I love it. Fantastic. Awesome. Let us keep going. So we got some subtraction here. Interesting. Okay. So if I've got, let's see here. So we start here with v. I go over 3 and up 2. Boom. There is v. I've been forgetting my little. And now with w, so that's minus w or negative w, okay? So we're going to go the opposite direction. I'll stop with the Harry Styles. Well, I'm going to go the opposite direction there, one direction. And I'm going to go to the left 2 and then up 2, which would end me right here. that would be negative W. Okay? So before I was going to the right 2, so now I'm going to the left 2. And before I was going down 2, so now I'm going up 2. Okay? Right? Pretty straightforward as far as that goes. Makes sense, I think. Hopefully it makes sense for you. And now my result vector, I'll use bright pink here, would be this one right here. This would be our V minus W. Yay! Fun drawing vectors, right? So fun. So you may have been asking yourself, you're like, hey, does vector addition have the same properties as our usual addition that we've known since like 2nd grade or whatever? Maybe 1st grade? I don't even know. But yes. So vector addition is commutative. Okay? V plus W is equal to W plus V. Notice those are bold letters. They don't need the little arrow. Vector addition is also associative. So we can group them differently. Right? That's what associative is. The 0 vector has the property that the vector, say, V plus 0 is equal to 0 plus V, which is equal to V. So that holds. And then V plus the opposite of V, negative V, is equal to 0. Awesome. Fantastic. How great to have that. And we've also have the graphical representation here, where you can see that W plus V would give you the same as V plus W. All right? I like it. And you can also see that with the V and negative V there as well. I think those are some lovely little graphics. So there are different types of forms of these vectors here. So we have what's called a component form here, where we'd have A, comma, B. And those are not parentheses. Those are, okay, they are jagged. Okay? Wonderful. Awesome. So we can write it in that form. Whoa. Sorry, I had a brief malfunction there. We can write in that form by looking at our direction, or the distance that we're moving in the X direction and then in the Y direction, right? The horizontal and then that vertical direction. That's pretty much all there is to it. But we do like to write that out in a little more fancy math terms. So if we have the point P sub 1, okay, and then the terminal point P sub 2, so initial point's P sub 1, and then terminal point is P sub 2, as we see. That's over here, okay? Whoa. What's going on here? There's my marker. There it is. Okay. So that's what we're looking at. Now, to get that component form, or position vector, as it was also referred to, we could take our X values, the X value from the second one, the terminal point, subtract the X value from the initial point, and then do the same with the Y's. That's what we have illustrated right here. And that will give us our component form, or position vector. Okay, it'll give us 2 values. So in this case, it looks like it would be I don't even care what the number, I'll count them out here. Be 4, this would be 3, so this would be written as 4, 3. There we go. Awesome sauce. If I actually wanted to count those all the way out here, that's a lot of counting, but you would take this X value from P2, subtract this one to get you 4, and then you'd take your Y value, Y sub 2, subtract Y sub 1, and that would give you your 3. All right? Lovely. Awesome. Fantastic. So let's find our position vector, or put it in component form here, and we'll plot it here on the graph. So we want, we've got, the vector is going to be P sub 1, P sub 2, and we will, so P sub 1 is -5, -3. Awesome. So that's our initial point. Then our terminal will be -4, +1. Cool. So if I draw that out, now, if we want to work it out as, let's see here, we would have our x2, which would be -4, minus -5, comma, and then y2, 1 minus -3. That's going to be, let's see, it's positive now, so it's going to be 1, comma, and then 4. So that would be our component form, or our position vector. Now, let's take a look. Let's take a look at it graphically. I went over 1, up 4. That checks out, right? From my initial point to my terminal point, I went to the right 1, I went up 4. Boom. Awesome. Fantastic. I like it. All righty. Just realized we did part 2 there. From the initial point to the terminal point, determine the horizontal and vertical movement. That's what we did. And then the work, that would be our work right here. And our answer would be the 1, 4 here for our vector formula. Again, you see how they're jagged, right? They're not parentheses. Lovely. All right. So let's see here for this one. Find the position vector. So this time it doesn't give us like a graph to really look at it. Find the position vector v with the points 4, 2 being your initial and then 2, 3, 2, -3 being your terminal, and leave it in component form. So let's see here. We would have x2, so 2 minus x, minus x1, comma, and then -3 minus 2. Beautiful. And I'd end up with -2, comma, -5. And how about we look at this, because I think a graphical approach is always helpful. Let me pop a graph on here. And let's plot these points. So I'd have 4, 2, so 1, 2, 3, 4, 1, 2. So this is P sub 1. And then we have 2, -3, 1, 2, 3. And let's see here, we're going to the left 2. That checks out. We're going down 5. Boom, that checks out. I like it. I like it. Beautiful. Fantastic. Awesome. Very good. But wait, there's more. All right. So we can also write vectors in terms of I and j. I not being the imaginary I. Something different. Okay. So a vector, first off, a vector with length 1 is called a unit vector. Okay. So for example, vector W being 3/5, comma 4/5 is an example of a unit vector. If we were to find the magnitude of that vector, it would be equal to 1. That's considered a unit vector. All right. We have two special unit vectors, I and j. I is a unit vector, a length of 1, in the x direction, or a magnitude of 1 in the x direction, and j is the unit vector, magnitude of 1 in the y direction. Okay, we can see that right here. Okay, there's your I and your j. Lovely. Where was I? Okay, so I would be 1, comma 0, and j would be 0, 1. Okay, and then we've got our magnitudes. We said the magnitude is going to be 1 for both of those. So therefore, we can write our vectors in another form here. So the vector v being AB, in the x direction, it is going A. Okay, and if I multiply that by the unit vector for the x direction, 1, comma 0, and the same for the b for y, so this is my up and down movement, right? Okay, then I'm going to have a times, let's use some substitution here. I can substitute I in place of that. So I'm going to have a I, and then I would have, substituting in the j for this spot here, this is 0, comma 1, right? The unit vector in the y direction. I'm going to have b, comma j. So that's my general form when writing it that way. So sometimes you'll also see them written with a little hat over them. So I hat, j hat, it can be read out as. So that way you don't get it confused with the imaginary I. Lots of new stuff here. So we might see it just in that component form. We may see it with the I hat, j hat form, right? All great to be, well versed in the world of vectors. All right, so let's let v equal ai, a sub 1 I, plus b sub 1 j, or we'd have in our component form our a sub 1 comma b sub 1, and w will be our a sub 2 I plus b sub 2 j, or a sub 2 b sub 2. So those are our two vectors, and we're going to have alpha be a scalar. Then these following properties would apply here. So we'd have v plus w. We can just add our a components together and our b, and we would result in a sub 1 plus a sub 2 equals b sub 1 plus b sub 2. Imagine those as being numbers. So what if I had this? 2, comma 3 for for v, and then let's say w was, I'm going to go with negative 5, comma 1. Well, then we add those together. I would just add my x direction and my y directions together. So if I'm going to add these, as that example has, then I would have 2 and negative 5 would add together to be negative 3. 3 and 1 would add together to be 4. That's it. Okay? So sometimes like the nice written out math way is a little bit overwhelming, a little bit scary, a little terrifying, and it's not too bad. So for the next one here, for subtraction, we can do the same type of dealio. So if I have the same ones, but now I'm subtracting those vectors, I would result in, well, 2 minus negative 5 would be 7, and 3 minus 1 would give me 2. Cool. I like it. Wonderful. Fantastic. Awesome. And now if alpha is a scalar there, alpha times that vector v, I would multiply that alpha into your x direction and your y direction as well. And we would end up with, let's do an example here. How about, let's say I had some number 5, and then we had 2, 3 for our vector v here. Well, my result would then be 5 times 2 is 10, and 5 times 3 is 15. That's it. Cool. So you'll find that the operations with these is it's pretty straightforward, but there's a lot to remember here. And then the last one, that's our magnitude, right? We've already dealt with the magnitude, but hey, we're already here. Might as well, with my example here, I would have the square root of 2 squared plus 3 squared. That's 4 plus 9 is 13. That would be my magnitude of v. Sometimes you'll see it with 1 set of absolute values. Sometimes you'll see it with 2. Love them. All right. I like a couple of these graphics. I'm going to actually zoom in down here on this one for showing the addition here. So for my, when we were adding the two vectors, v plus w, again, I'm just adding my x components together. So you think about this length of 1, 2, 3, 4 here. And then for a2, which was our with our w vector, 4 plus 3 gives me 7, so I'm moving a total of 7 in that x direction. And the same idea for the y direction, where I went 1 for b sub 1, and I went 6 for b sub 2. So that together, I think it went 6. Nope, sorry, I went 7 there. So add them together for a total of, it looks like 8 on this one here. Sorry, I misspoke, miscounted. All right. Nice little graphical representation. You can show that with the other ones as well.